Thank you. So the paper I'll be so like he said, I'm Sarath, and the paper I'll be presenting is called Handling Model Uncertainty and Multiplicity in Explanation via Model Reconciliation. So sorry, it's a mouthful. It's a joint work with Tathagata, who's in the audience, and Rao. So this work is in fact an extension of an earlier work we had in defining what we mean by explanation via model reconciliation. So that appeared in ICAPS 17. So before I get into the details of this paper, I would like to take a few minutes to really try to give an intuition behind what is explanation via model reconciliation. To start with, one of the focuses of classical planning is looking at the problem of generating plans that allows an agent to achieve a pre-specified goal. So, but unfortunately for an agent to be truly successful in real world, it's just not just enough that they are capable to achieve goals. They need to be able to coexist with humans. And that requires these agents to be human aware, which means they need to be able to adapt to the beliefs and expectations of the human. This means that we need to not only model the capabilities of the robot, but also the human's expectation about the robot's capability. So this figure kind of sums up the thing. You have the robot with its model, which is, should have been MR, but sorry. And then you have the human who has some expectations about that model. So the question is, what happens when these models diverge? So basically now, when they diverge, the robot's optimal plan may not seem optimal to the human, or even safe for that matter. So in such scenarios, what should the human do? Okay, the first thing they can try to do is try to create what we call an explicable plan. The robots can act in a way that seems more in line with what the human expects, but that comes at a cost on the robot's side. The other option is so it may not always be feasible. The other option is the robot can stick to its optimal plan and then try to explain why that plan is optimal. So, but these kind of explanations cannot be a soliloquy. It has to explain with respect to the human's model. In our formulation, we see explanation as a process of bringing models together. So the actual contents of the explanation itself would inform the human about the changes in the model they need to imbue into their own model so that the current plan can be properly evaluated. In the ICAPS paper, we formulated this as a search of a space of possible models. But we made two big assumptions. One was that there was only a single human observer. The second one was that we had a complete and correct representation of that observer. And through this work, we are trying to relax both of these assumptions using a single approach. So through this work, through this talk, I'll try to present how we are trying to create explanations when we only have an incomplete model of the human, and we will show how the multiple human setting can basically be compiled down to this setting with incomplete models. So to start with, we'll talk a little bit about what I mean by incomplete models. So why do we need incomplete models? So it's rare to ever have a scenario where we know what the human expects of us. So you could always say that such humans' expectations can be learned. Like there are a lot of work in ICAPS community and outside where we are learning planning models. So you could say we could learn such models. Unfortunately, learning mental models is a lot harder than actually learning the model of a specific task, because we can not really get a lot of I just jumped. Okay. So we can't get a lot of plan traces which we can use to learn such models. At best, we will have to interact with the human to get information about these models, and that can be quite expensive. So usually what you end up with is you might be able to learn about certain parts of the model. So you would know that these action has these preconditions and effect, but there will be other parts of the model you don't really understand. So you don't really know what their preconditions and effects are. So we will represent such models with uncertainty as an action definition with annotated possible preconditions and effects. To see what I mean by that, here is an example of one such model. If you see, you can see, you can see that here there are two possible preconditions. So this is a pickup action from your standard blocks world domain, and you can see there are two possible preconditions. One is the hand empty, and the other is the block is light. So when I say that there are these two possible preconditions, this in effect means there are four possible actual definitions. And the actual model can be any one of these four. And we will refer to these possible instantiation as the completion set for this incomplete model. So how do we explain in such a setting? Basically, explanation here boils down to the fact that the human's model is one of these completion set, and we need to come up with an explanation that would work for every model within the completion set. That would allow and ensure that the plan is explainable to the human after our explanation. Okay, but this could seem like a very daunting task. We need to go through each one of the individual models and see what explanation would work for all of them. Thankfully, we can exploit the structure of these annotated models to simplify the process. We'll specifically focus on two models. One is called the max model, which is the most relaxed model in the set, which we can get by only considering the possible adds and then ignoring the possible preconditions and deletes. And then you have the min model, which is the most constrained or least relaxed model, which you can get by doing looking at the opposite. So you consider all the possible preconditions and deletes and ignore all the add effects. So if you're assuming there are no negative precondition, that basically means any plan that's executable in min model is executable throughout the completion set. Okay? And any plan that's optimal in max model is optimal in any of the models where the plan is executable. Easy enough, right? So now explanation is about finding those model updates, which when applied to the original incomplete model would result in a new incomplete model where the plan is executable in the new min model and the new optimal in the new max model. So this will ensure that whatever models remain in the completion set, the plan is optimal in all of those models. This again can be seen as a search through model space. So you will start with the human's annotated model and then look for possible changes you can make to the set. And as soon as you reach a possible model where your required conditions are met, you'll stop and you will give the path to that model as the explanation. So the actual explanation would be in English, but the content would be something like this. You will basically tell the human about the changes in the model they have to make. That it would be in terms of the preconditions that need to be removed, the preconditions that need to be added, the effects that need to be changed, and so on and so forth. Unfortunately, since we are updating on an uncertain model, this could contain redundant information. For example, in this sample explanation, in fact, the human may already know that A1 does not have precondition P1. So you're giving them redundant information. So one way of getting around this is possibly weighing different model changes differently, so that you give more cost to cost to changing parts of the model that are uncertain versus changing the parts that are known. But that doesn't completely solve the issue. The other option is to have what we call as the contingent explanation. Basically, you will have sensing actions, which corresponds to these uncertain parts. And you will only give explanation with respect to the known parts. So this just basically turns into an AO star search problem. And that should read, and nodes correspond to sensing actions. So you can also play around with the cost of these nodes to get different behavior that you want. Here we looked at the possibility where we didn't really care about the total cost of the explanation, but we were looking for selecting explanation which had a possibly short explanations. Right? Like when sometimes you know about something, you can just directly give a very simple explanation. So we were looking at possible costs we can use to generate that kind of behavior. We also looked at other approximations that was basically in regards to the speed up of the search. So one thing we looked at was what if we did a search under the assumption that we knew the model. And once we find a solution, we can look at the kind of assumptions we made and then use that as a test. Okay, so if all the assumptions are correct, we return the solution, or we'll use the answer to these assumptions to update our queue. Sorry, I'm not going into a lot of details, but we can always discuss offline more about the exact approaches we used. And then here we did some standard like evaluation on the performance of the various algorithms we discussed on like some standard IPC domains. And one of the interesting things I wanted to show you was like here we compared our approach on solving incomplete models with, these are the completion sets, with the size of the completion sets. So we had incomplete models with increasing number of like more increasing uncertainty, and then we actually compared it against, what would be the cost of running our original explanation algorithm on each one of these models, and then just doing like a union. So clearly our approach provides us a lot of computational advantage, as you can see. So now, coming back to the multiple human observer case, now you can see a parallel, right? There we had an incomplete model that correspond to a set of possible models. Here we start with a set of possible models. So the idea is we take a set of possible models, convert it into an annotated model, and then run the same algorithm. So basically a simple way of coming up with such annotated models would be to do like a intersection among all the models. So all the common parts become the known part of the model, and the rest become the annotations. Okay, so here we have like a demonstration of our approach on a physical robot. Thank you. So we have a situation with 2 humans and 1 robot. So this is an urban search and rescue scenario. So one of the humans is an external commander. So the only thing they can do is they can select the goal that the robot needs to do, and they can then like basically monitor the plan at a very high level, and also can ask for explanation and stuff like that. The internal human is actually in the scene along with the robot. So internal human has a slightly different map from the external human. So because he can see what changed and stuff like that. And he's supposed to participate in the plan. So here is, and the plan basically involves going for the robot to, the robot to go and collect a package from the internal human and then go to a waypoint. So here is the basically our system in running. So just to give you guys a note, in this, when we were running this actual experiment, the external human was in New York, and the rest of the people were in the Arizona, like in ASU, and people from US would know that quite far. So the person in New York, which was Tathagata, only had access to like an SSH terminal, and they could like set the goal and see the plan. So basically now the robot is planning. Sorry. It presents the plan and the explanation here. And the human understands what changed. So he asks the internal human to go to the fixed waypoint according to this plan. The robot goes to the waypoint. Yeah. And I'll just skip ahead. So it presents the same information to the internal human. Thank you. It collects the package, and I think we can just skip ahead. Sorry, I paused it. Okay, and then it collects. Takes a while to collect. Sorry. Yeah, it collects the package, and then it's on its way to the final goal. Okay, so that was our approach to handling explanation with uncertain models or multiple observers. So there are a lot of future work we plan to do on this direction. One is obviously performing actual human studies to validate our method to make sure that we are working properly. though the core concept of model reconciliation, we've already done separate studies to validate those. But we would still like to see with incomplete models how these approaches work. Next is extending these methods to stochastic model. And the other big challenge is, I assume that we are starting with an annotated model. So in the worst case, these annotated models could contain all possible models, but those could be really inefficient. So we also need ways we can bootstrap or learn these annotated models from some traces and then refine them through interaction. So that's my work, and I'm looking forward to questions. Sure.
Have you performed any validation that the approach of explaining or model reconciliation is effective using this approach?
So this, like I was saying, is an extension of an original approach. That approach, we've done some user studies. And it's basically, at least our results seem to imply that it works well enough. People expect these kind of explanation. And also when we ask people to give these kind of explanation under resource limits, and their own explanation kind of lines up with what we were expecting. So the ones with multiple models and model uncertainty, we haven't done user study, but we are setting it up. It's a little more complicated user study, so we are working on making sure that it's properly set up. Thank you.